Looking at this next example, it says it's given us a polynomial at the top. It says using remainder theorem, find the remainder when p of z is divided by z minus I. And then the second part is find the remainder when p of z is divided by z plus I, so it's conjugate. So before we start anything, we need to understand what the remainder theorem is. So the easiest way to understand remainder theorem is, let's just say we've gotten, so what is the remainder theorem? It's basically just saying a simple polynomial is divided. So let's just say f of x in this case, make it a little bit easier for ourselves to understand what I mean. F of x is divided by some random polynomial. We can say x minus c. X minus c multiplied to the divisor, multiplied by the quotient q of x, plus remainder r of x. In this case, if x minus c has a degree of 1, so let's just say d of x has a degree of 1, the remainder is always going to have a degree of 0. So it's going to be some constant in this case. So if d of x in this case, which is x minus c, has a degree of 1, the remainder is always going to be 1 less than that. So r of x then has a degree which is just going to be some constant r in this case. Looking at that, let's just do a little simple proof to get an understanding. If we let f of c, what do we get? F of c then equals to c minus c multiplied by q of c, plus r. In this case, so remainder, remember, is just a constant. This then gives me 0 multiplied by q of c, which is just 0, plus r. Therefore, f of c then equals to r. Remember this. This will help us in this question right here. So let's just come back. I'll leave that up there just so that we get a better understanding. Or I'll just write it up at the top as one final note to ourselves. Given x, f of x is divided by x minus c, we can just go f of c then equals to remainder r. So we've got that. Let's come back to this. We've got our polynomial up here, p of z. So p of z, it's asking using remainder theorem, find the remainder. In this case, we know z minus I. Z minus I is also the same as x minus c, correct? So the term we're going to sub in instead of the z is going to be z equals to I, correct? Z equals to I, same as x equals to c. So there, you see this. So this then interrelates with, if we sub in I, we're going to get our remainder right here by remainder theorem. So I'll rewrite all of this again. Z cubed is, for clarity, is 2z squared plus 3z minus 1. Correct? Add sub in I. P of I then equals to I cubed minus 2i squared plus 3i minus 1. Yep. I cubed is just minus I. Minus plus 2 plus 3i minus 1. So this then gives me 1 plus 2i is your remainder for this one over here. Now we'll go on to II. II says same thing, but this time we're dividing it by its conjugate. So this then gives me z equals to negative I. So p of negative I is the conjugate of p of I, correct? So we can rewrite this as p of I with a little bar on top, denoting that it's the conjugate. Same thing, if we know what P of I is, which is just 1 plus 2i, bar, which is just 1 minus 2i. So that is the remainder theorem and those examples over here. This example right here says, again, given us a polynomial, ai, given 1 minus 3i is also a 0, is a 0, explain why 1 plus 3i is also a 0. Second, find the third 0 of this polynomial. And then the third part is write P of z as a product of linear factors and linear and quadratic factor with both real coefficients. So before we start anything, we're going to need factor theorem later in this. So let's just begin with what a factor theorem is. A factor theorem suggests that given f of c, coming back to that same example, f of c, if f of c gives you a 0, gives you the value of 0, you know x minus c is going to be a factor of f of x. That is pretty much it about a factor theorem. If, again, x minus c, if c gives you the value of 0, you know that that is going to be a factor of f of x. So yeah, just a little note to ourselves. We'll start with a. It says, if it's given us our first root, which is 1 minus 3i is 0, explain why 1 plus 3i is also 0. In complex numbers, if a polynomial has real coefficients, we need to straight away know that it's going to have a conjugate. So if, obviously we know it's got a real coefficient right here. So this then, if we just write it down, 1 minus 3i is then going to be a factor. So then the conjugate is actually going to be a factor. So 1 minus 3i bar would then give us the second root, which is telling us why. Because it has real coefficients. Relatively straightforward. B, third root. We already have 1 minus 3i, 1 plus 3i. Sorry, we'll write that down. 1 plus 3i, 1 minus 3i. Sum of roots to solve for the third one. We know we've got 2. We need to find the third one, so we can get alpha plus the first root, 1 plus 3i, plus 1 minus 3i equals to minus b on a. Minus b upon 2. Minus b is a, b, c, d. Minus b, negative 3 upon 2 is just give me 3 on 2. Correct? 3 on 2. Solve for this. Alpha plus 2 alpha plus 2, 3 out chop, 3 upon 2, alpha then equals to 3 on 2 minus 2, which is going to be 1 upon 2. Negative 1 upon 2 is the third root. Gotten the third root, let's do part I, linear factors. First root we have z equals to minus 1 upon 2. We have z equals to 1 plus 3i, and we have the third one is z equals to 1 minus 3i. Rewrite this, we have 2z plus 1, first root. We've gotten z minus 1 minus 3i, second one, and then the third factor is z minus 1 plus 3i. Rewrite this. So P of z then equals to, we can factor out the 2 out, 2 brackets z plus 1 upon 2, correct? Z plus 1 upon, right, a bit bigger, z plus 1 upon 2, because 2 said and then yep. Second linear factor would be z minus 1 minus 3i, correct? And then the third one would be this one here, z minus 1 plus 3i. Those are the linear factors right here. Now we just do the quadratic one, linear and quadratic, so we can go rewrite this as 2z plus 1. We have z squared, I believe would be z squared minus 2z, yep, minus 2z plus 10. So that is your final answer for 3 right here.